Philips research headquarters are located in Eindhoven at the high-tech campus, where technology partners benefit from a spirit of open innovation that allows access to facilities, people and networks. As a further step in fostering open innovation, Philips has established MiPlaza, a centre for microelectronics and nanotechnology. At the core of the MiPlaza facilities, a new state-of-the-art cleanroom is located. With its 2,650 square meters, the new MiPlaza cleanroom ranks as one of the largest research cleanrooms in the world. This cleanroom is a multi-purpose, multi-technology Class 110,000 facility. It offers a broad range of process equipment capable of handling substrates of any shape, in sizes up to 200 millimeters. The MiPlaza cleanroom will be used by Philips for its internal strategic innovation programs, concentrating on topics such as materials and devices for molecular medicine, solid-state lighting, system-in-package solutions for healthcare, lifestyle and technology applications, sensors and actuators, and new types of displays. These will all benefit greatly from the broad range of materials, process technologies, and the professional engineering crew. For making a micro or nanoscale device, the typical processing order is 1. Deposition, 2. Lithography, 3. Pattern transfer by etching, and 4. Measuring and inspection. Here, a batch of silicon wafers is loaded in a sputtering machine. In this case, a thin metal layer is deposited. For depositing a thin film coating, a range of technologies is available. A great variety of metals, alloys and inorganic components can be applied. We have over 150 materials in stock. Ion implantation can be done to modify the electrical properties of a material. High-energetic ions are generated and accelerated towards the substrates. Like most of our machines, this implanter is able to handle standard-sized silicon wafers, as well as other substrate materials and sizes. Annealing of wafers is done in well-controlled high-temperature furnaces. Here, a batch of wafers is carefully placed in a quartz loader. They are automatically loaded in the furnace tube, which in its interior can have temperatures as high as 1200 degrees. Photolithography is used for patterning the thin film into a microstructure. At first, a UV-sensitive photoresist is spun on the wafer, while rotating the wafer at very high speed. This process is followed by baking out the resist in one of the hot plate stations. Subsequently, the resist is locally exposed by UV light through the open areas in a mask. This exposure is done on a contact aligner or on a stepper. For making nano devices with details smaller than 100 nanometer, electron beam lithography is used. Here, the resist is not exposed by light, but by electrons. By using a spot size of 4 nanometer, very fine details can be fabricated. The wafer is loaded in a high-precision cassette. The wafer position is scanned, followed by writing the pattern by the scanning electron beam. After lithography, the pattern must be transferred into the thin film by means of etching. 70 wet benches are available for wet chemical etching. Here, an automatic etch line is shown in which a batch of wafers is etched, rinsed and dried. For resolving the finest details, anisotropic etching is needed. This is done by reactive ion etching, in which the removal of material is done in a vacuum system. Via a load lock, the wafer is transported into the reaction chamber, in which a combination of physical and chemical etching takes place. The reactor is equipped with an optical system to detect the end point of the etching process. The final product can be inspected through a microscope. However, in micro and nanotechnology, the high-resolution structures can only be imaged in a scanning electron microscope. Here, a sample with nanowires is observed. A finished wafer with the micro or nano devices can electrically be evaluated on a probe station. The wafer is scanned by a probe card with a parallel set of probe needles. In this way, vital information about the preceding processing can be obtained. This step is an important link between thin film processing and device performance. In order to stimulate open innovation, the clean room facilities of MiPlaza are also offered to third-party researchers and engineers active in the field of materials, devices and microsystems. These institutes and companies not only benefit from major cost savings that come from sharing facilities, but also from the stimulating cooperative atmosphere and know-how concentration at MiPlaza.